Hello. Okay, I'm gonna walk through the process of the synthesis challenge real quickly because I think a lot of us got a little stuck on that problem or didn't have enough time to finish it all. So I'll start off by just indicating some of the most important formulas that you're going to be using here. Over here, so we have the formulas that you determine on the second to last activity, which are going to be the formulas for what integer or what values of wavelengths does a path length difference need to be, such that you get either maximum constructive or deconstructive interference. So for max constructive, you ended up getting that you needed a path length difference equal to an integer value of wavelength. For max deconstructive, you end up getting that you need a path length difference equal to your wavelength times an integer plus 1/2. And remember, we have this plus 1/2 because we want to be at half integer values of lambda, which I kind of showed with the transparent sheet and the two interfering waves. If you're having difficulty with that, I'd say refer back to that section of the lab. So we have these two formulas. We know that we're eventually going to be solving for the frequency of the sound coming out of the two speakers. And so how do we solve for frequency? How do we get frequency from any measurements we're going to make or from these formulas? I think it's helpful to remember this formula that we talked about last lab, which is wave speed is equal to your frequency times lambda. Okay, this is awesome. Because now, if we're able to find this lambda using these equations, we can just plug it into here to solve for our frequency. Better yet, we know that this sound is traveling through air, and we know that the speed of sound in air, this guy, is equal to 343 meters per second. So that's going to be our speed of sound in air. Awesome. Okay, so let me make sure we're in frame. We are, this is awesome. Okay, so we have over here, I'll draw kind of a picture of the scenario. We'll have this be speaker 1 and this be speaker 2. And so these are both emitting sound waves and they're interfering. You walked around the classroom and you were noticing sort of louder and quieter spots. I think there was some difficulty determining what a loud and quiet spot is. So in terms of the language that we learned today, those loud spots are going to be anything along a maximum constructive interference line. If we think about the simulation, those would be the lines along which there was a lot of high contrast, really bright blue and dark black spots. Places where a peak and a peak are intersecting or a trough and a trough. The quiet spots are going to be any line that's along a maximum deconstructive interference line or a nodal line. And so those are going to be what kind of the fuzzier, lower contrast lines were on the simulation, or any spot where there's a peak intersecting a trough or a trough intersecting a peak, vice versa. So if we're just thinking about sort of the pattern that we saw in the rest of the lab, we kind of saw, yes, these have waves going out and these have waves going out. We saw that the peaks tended to intersect in the center, and then there was kind of a quiet spot, a nodal line, and you had another loud spot where peaks were intersecting again. So I think that would be a good way to expect what is going to happen in the classroom. I think some of you had a hard time finding it. That's totally okay. It's kind of a tricky measurement to make. But at least when I was doing it, I found that there was a pretty consistent loud spot. I'm just using an L to designate loud, down the center right in between the two speakers. And then I found that as I walked this way and this way, I kind of ran into different quiet and loud spots. And so I kind of noticed a quiet spot a little further out, kind of going inwards, quiet spots here. And then it got back to loud and back to loud. And so the reason why I'm kind of focusing on going horizontally rather than vertically, if you remember from the interference patterns we looked at, those lines seem to kind of emanate from the center and be maximum constructive all the way down, be maximum deconstructive all the way down. It didn't really go loud, quiet, loud, quiet, loud, quiet. It was all loud, all quiet. If that part is a little bit confusing, that's something else that we can talk about. But this is generally the pattern that you should have noticed, and this is what we can kind of piece together, even if we weren't hearing any sound, like even if we were just using the transparent sheets to try to figure out where things might be. So, okay, we have these spots. Let's say that I found this spot to be just like really good. I could really tell it was a quiet spot. Awesome. What do I do now? If I have my little person standing right here, what should I do? Given that our formulas have path length difference, and that's something that we can just measure with a ruler, that's a really good next step. So what I did was I measured my distance from source 2 to where I am, and I measured my distance from source 1 to where I am, and we'll call this R2, and we'll call this one R1. These are going to be different distances. I'm clearly further away from source 1 than I am from source 2. The reason why, by the way, I chose a spot that's not on like that center loud line, which I think a lot of you did think to choose, is because of how we designate our n values and also how our delta r works. If I was standing right here, per se, the r values would be the same to both. I'd be the same distance because I'm directly centered in between them. So we'd have a 0. And then, I'm not sure if you guys know this from class, but if not, this like maximum constructive interference line down the center, this line is our n equals 0 antinode. This next line, this quiet spot, this is our n equals 0 nodal line. And then the next loud line over, this one here, this is our n equals 1, this one here, this is our n equals 1 antinodal line. So it kind of starts at 0 in the center, in between the two sources, and then fans outwards, increasing by integer values. So sometimes this is referred to as the n equals 1/2 antinode. I prefer to refer to it as 0 since we have this like 1/2 wavelength already included in our formula. We don't want to count that in twice, if that makes sense. So I didn't choose a center spot because I would have now a 0 equals 0 wavelength. Obviously a 0 times a 0 is 0, so this really could be anything. I'm not getting a lot of information about my wavelength then. So I say, okay, I'm not going to choose something on the n equals 0 line. I think that this is a great spot to go though. I'm going to choose my quiet spot. And yes, it is n equals 0, but our deconstructive formula, which we use because it's quiet and not loud, has this 1/2. So I won't be having a 0 equals 0 times lambda. I'll be having some number here equals 1/2 times lambda. Cool. So the measurements that I got were my R2, which is this value here, was equal to 1 meter. My R1, which is equal to this guy here, was 1.5 meters. Sweet. And yes, okay, just had to make sure I had those values right. Okay, so now I have my R2, I have my R1, and I have my n value. So now I'm gonna go ahead and use this equation and solve for my lambda. So we have again, delta R equals n plus, I don't know if you guys can see this actually, let's see. Ooh, not quite, I'll turn ya. Okay, sorry about that. So we have our delta R equals n plus 1/2 lambda. So let's plug in our values real quick. We have, well actually, let's rearrange first. So if we rearrange this to solve for lambda, now we have that lambda is equal to delta R over n plus 1/2. Okay, we know our delta R is going to be equal to this value minus this value, and we know our n is equal to 0 on this first nodal line. So we have lambda equals 1.5 minus 1 over 0 plus 1/2. This works out to 0.5 over 1/2. This all works out to 2 times 0.5 works out to 1. Okay, so 1 meter. This means that our lambda is 1 meter. Awesome. I'm going to rewrite a little bit. I'm going to erase this part right now. You'll be able to go back in the video and find it, so sweet. Okay, so now that we have that lambda is equal to 1 meter, I'll write that up here. Sweet, we have this information. Now, how can I use this to solve for frequency? Because frequency is what we ultimately want. We can use this equation here. So we can rewrite v equals f lambda to solve for frequency, so that its frequency is equal to wave speed over lambda. Good. Okay, and like I said here, our wave speed, the speed of sound in air, is equal to 343 meters per second. So we can write that our frequency is equal, sorry, this pen is dying, is equal to 343 meters per second over this 1 meter right here for lambda. These units cancel out, that's awesome. And so we're left with a frequency of 343 hertz, which is just 1 over seconds. So this is pretty close. We had a, I think we had set our frequency to a little above 300 hertz, not quite this much. So it's not a spot on measurement, it's not perfect, but but for, I think, the accuracy of our measurement tools, just with a ruler, I think it's pretty close. Our rulers sag a little bit, so we don't get perfect measurements. And of course, we aren't necessarily always right on the nodal line, and that's another issue. But this process is correct. If we had perfect measurements, we should get around 300 hertz. Yes, I apologize for how chaotic the end of lab was. And if you have any more questions that this didn't answer, please let me know. Hopefully it was helpful. Thank you guys.